Hubble sees the ordinary, boring part of the universe, and we see the 10% of the universe that is seriously effed up. Right? The exploding stars, black hole, all the really interesting stuff that is completely invisible to Hubble.
Right.
In a lot of cases. And so, because when matter is at 1,000,000 degrees, it shines really bright in X-rays, but it's transparent in visible light. And so you just see right through it, right? And so that's the bullet cluster there. There's a black hole shooting out jets at the speed of light. And this is an exploding star, freshly baked elements.
Wow.
And so, one of the things we've discovered, just to say that, the bigger, not what I work on, but the fact that carbon is common and gold is rare, right? We understand why that is now, and it's to do with nuclear reaction rates in stars.
Really?
Because every atom in your body was baked in a star, right? And then the star blows up, and the Earth forms from the ashes. And so, which elements are common, and we can even tell which elements were mostly made in which kind of star, and things like that. And so that's why. So it's really, we're studying our own origins. That's my office that I used to be able to go to before COVID. Everyday features of the world around us are intrinsically tied to things in deep space, because you and I are made of stardust.
Right.
In a very literal sense.
So, Jonathan, I admit I definitely want to have you back on to talk about your work, because that was seriously what I really intended to get to in the back half of this, and we ran out of time. I really do want to have you back on to talk about that, but I think there would be an absolute revolt in chat if I did not ask this final question.
Oh no.
The Karman line, pro or con?
Well, and we're out of time, folks. How am I supposed to display this? This is not to scale nonsense. Like, hang on, we'll start down low.
But basically, for everyone out there, I'm sure you're all familiar with this, but there is this sort of idea that space begins at 100 kilometers. But Jonathan, I know you are a proponent that it's not as cut and dry as that.
Right. And really the idea, so Karman in the 1950s came up with this idea that called the Karman line, which was that you should define the boundary of space where basically where orbital dynamics was more important than aerodynamics, right? And that's the big picture. And over the year, the initial estimates of that were around 80 to 90 kilometers. And then over the years, people sort of felt like you couldn't define it very accurately, and so why not just pick a big round number,
right?
And pick 100, because we're metric and not medieval. And so, and so the 100-kilometer number became associated with the Karman line. The point that people started thinking that was its definition, but historically that's not true at all.
Okay.
And so I went back with modern atmospheric models, and modern and 50 years of data of actual satellite orbits, and tried to ask, okay, if you ask Karman's question, what number do you come up with? And I came up with a number that's like basically 80 plus or minus 10 kilometers is where and the plus or minus 10 is depending on whether if you're asking whether aerodynamics is more important than the gravity, the aerodynamics depends on your ballistic coefficient. It depends on whether you're a sail or against cannonball, right? And so if you're a cannonball, the Karman line is lower. If you're a sail, it's higher, right? But only by like plus or minus 10 kilometers.
Huh.
Yeah.
It's actually surprisingly, and solar activity doesn't move it hardly at all, it turns out.
Okay.
And so I went into all of these things. Like, actually, it's much better defined than I had expected when I started the study. And therefore, 80 is a pretty good number, is what I'm arguing, and that 100 is, from the Karman argument, if you want to use the Karman argument, 100 is too high. And so 100 is only good if you just like round numbers and you don't want to bother about the physics. So that's my my claim. So I'm calling it the effective Karman line, or whatever you want to call it, at 80 kilometers. And this started because I was making lists of astronauts, and I wanted to know who should I include in my list of astronauts. I was making lists of suborbital rockets. So I want to know what should I include as space launches, and so I had to pick a number. To make my list, and so, being the obsessive mathematician that I am, I went down the rabbit hole of what number should I really pick, and after many years of study, I taught myself atmospheric physics along the way and things like that. I came up with this answer, and that's the answer I use in the general catalog of space objects on my website when I'm listing whether things are in space or not, and I published a paper in Acta Astronautica with those results, and so it's formally refereed paper in the literature saying, yeah, this is a good choice if you're using that argument to say where should space begin. It should be 80 and not 100. And by the way, the idea that Karman equals 100 is historically very dodgy, and so that's the short version of that argument.
I like it. I was going to ask, why is defining this important? But defining it's important if you're saying what's in space and what's not in space, because we were talking about.
I had a need, right? You may not have a need. You may not care.
So you made an equation for it and figured out where it should be, right?
Yeah,
roughly.
Yeah.
Very cool.
But from that categorization standpoint of who's an astronaut, what made it to space? Because I think the big thing here too is we're not talking about what's in orbit, because orbits are not stable, at 100 kilometers either.
But right, another thing I go into my paper is I looked at what's the lowest perigee that things have multiple perigees at. Okay. And so if you have like a Molniya orbit satellite, right, that has a very elliptical thing. It turns out that there's a fairly sharp cutoff that objects can survive for weeks at perigees of like 90. But once the perigee dips below 80, it's gone. It checks in and it doesn't check out.
No kidding.
Right?
For weeks or for orbits, like some number of orbits, because you could have an orbit that takes a week, or you have an orbit that takes,
Well, typically these are like 12-hour and less orbits that are from these 12-hour communication satellites that are coming in, and so I looked at again 90 million TLE sets, and found the ones that had low perigees, and you have to be a little careful because actually NORAD sucks at doing these low perigee elliptical orbits, and you can't always trust them, so you had to do a little filtering. But we're hand waving over that. I convinced myself that the ones I could trust, you show that you definitely see a bunch of cases where the perigee is below 100, but you don't see any cases where it's below 80 and it still is in orbit the next day.
Yeah. And just to sort of final thing to sort of bring it back to something and connect this final question about the Karman line back to something that we're talking about earlier, this Shenzheng 5 core stage that will be coming back in uncontrolled. This is where it gets really dodgy in trying to figure out where over Earth it's going to come, because you could be stable below 121 kilometers. You could be stable for quite some time, or the properties could just cause you to come in on that particular orbit. And this is why it's not really clear to us until we're very close to it, right?
Yeah, for the circular orbits, like 130 or 120 is as low as you get before you come in. But then they don't break up until they get to about 70 or 80.
Right.
So there's enough drag to bring them in on that orbit, and then when they get to 70 or 80, they disintegrate. But then the problem is, right, so you're going around, you're skimming horizontally around the atmosphere at orbital velocity, and a little bit of weather, right, is going to affect you. And so if you are 1 hour out in your prediction of the reentry time, you are 18,000 kilometers out. You're halfway around the world, right?
Yeah.
And so that's why we almost never get reliable predictions of where something is going to come down.
Right.
Now, where you have to know very precisely when, and you never know it to that accuracy.
And that's why we want it to be intentional, like we were intentionally controlled, like in a controlled manner, deorbiting things at a targeted location, as opposed to skim around a little bit north of 100 for a while.
Instead of going circular 130, you're in 400 by 100, right? Now you're in an ellipse, which hits the atmosphere at a very specific point and doesn't come out again.
I like it. If anybody asks, 80 kilometers is like the Roach Motel of orbits. Like objects check in, but they don't check out.
Exactly.
So you can use that in a paper.